Okay, so damping material. Where do we find damping material? Only in pulse wave transducer. Okay, so damping material stops the ringing, cut down the number of cycles in a pulse, make the pulses shorter. Shorter pulses have broader bandwidth, low quality factor, and good quality images. Okay, so how short the pulse will be? Only 2 to 3 cycles. So a shorter pulse will have a very broad bandwidth. You see here, if I'm dividing by a broader bandwidth, operating frequency dividing by this huge bandwidth, I get a very small quality factor and very good quality images. Damping material has two negative effects: lowers the sensitivity and lowers the efficiency of the transducer. Shorter pulses will give you good images. Why? Short pulses have broader bandwidth, small quality factor, and good quality images. Only pulse wave transducers have damping layer that makes the pulses shorter, and only pulse wave transducers are used for imaging. Continuous wave is not used for imaging. Damping material lowers sensitivity and efficiency of the pulse wave transducer. Now, what is matching layer? From the name, you can tell it is matching two things, okay? So what is different here? The impedance difference results in reflection at boundaries. We already know this, that the impedance from chapter 6, we said whenever we have difference in acoustic impedance, we will have reflection. Transducer elements is solid and has an impedance that's 20 times higher than that of soft tissue. This will result in reflection of 80% of the ultrasound energy. Because of difference in acoustic impedance between PZT and soft tissue, a huge difference in impedance that's 20 times higher. The PZT has an acoustic impedance that's 20 times higher than that of soft tissue. If we do not correct this difference in acoustic impedance, 80% of the sound beam will reflect back and does not go through the skin, okay? To improve transmission of ultrasound wave, matching layer, how wide is this matching layer? 1/4 wavelength thick is placed on the transducer face. This material has an impedance value between that of the skin and transducer elements, okay? That improves the transmission through the skin. It improves the transmission, and we put many layers. Many layers will improve the transmission better than a single layer. Coupling medium or gel impedance is between the matching layer impedance and the skin impedance. The matching layer and gel, both of them do the same function, which is facilitate the passage of the ultrasound beam across the transducer skin boundary. If we put the impedances in order starting from highest going to lowest, it's going to be PZT, matching layer, gel, and then skin. So if we see here, we have PZT that has impedance, let's call it Z1. Z1 is 20 times higher than the impedance of soft tissue, that's Z2. We put the matching layer in the middle, and the matching layer has a PZT, let's call it Z3. It's a value between Z1 and Z2, mid-value between Z1 and Z2. That's how the matching layer managed to overcome the difference in acoustic impedance between piezoelectric elements and soft tissue, because itself has an acoustic impedance, a mid-value between those two. So Z3 is a mid-value between Z1 and Z2. And by overcoming this difference in acoustic impedance, the matching layer managed to facilitate the passage of the sound beam through the skin interface. How is the matching layer able to overcome the difference in acoustic impedance between PZT and soft tissue? Okay, transducer element is a solid material that have high density and have high sound speed, and it has an impedance that's 20 times higher than that of soft tissue. We have a great difference in acoustic impedance between PZT and soft tissue. Matching layer has an impedance of some intermediate value between those of the transducer and the elements. Matching layer is placed on the transducer face. The purpose of this matching layer is to overcome or improve the ultrasound transmission across the skin. It reduces the reflection of sound at the transducer element surface, and thereby improve sound transmission across. Multiple matching layers improve sound transmission. So how did the matching layer do this function? Because the matching layer itself has an acoustic impedance, a value between that of PZT and of soft tissue. The Z3 of the matching layer is between Z1 of the crystals and Z2 of the soft tissue. Z3 is an intermediate value between those two, and this is how the matching layer managed to overcome the difference in acoustic impedance and facilitate the passage of the sound beam through the skin interface. Where is the matching layer? In front of the transducer. How wide is the matching layer? 1/4 the wavelengths. What does the matching layer matches? The difference in impedance between PZT and soft tissue. How big is this difference? PZT impedance is 20 times higher than that of soft tissue. How is the matching layer able to match the differences in acoustic impedance between PZT and soft tissue? Because the matching layer has an impedance of some intermediate value between those of the transducer and the elements, transducer elements and the tissue. By doing this, the matching layer reduces acoustic impedance mismatch, which reduces the percentage of reflection and facilitates the passage of the sound beam through the skin interface.